everybody. Hello, everybody. Welcome to today's workshop. I think they are joining now. Let them join. Yeah. How many of them already? Thank you, Dr. Shankar. Thank you, Vinu. And thank you, everybody, for joining. Hello, welcome to today's workshop on T-test and Anova. This is something, which is always in our mind. Yes, Mania, Dr. Mania, good afternoon. It's always in our mind to understand the statistical analysis as much as possible as a researcher, because this is the thing which we need to, I'll not say master, but at least we need to have the workable knowledge on this particular area. And not only this, but the statistical analysis. And you must have seen our efforts and focus in terms of bringing this to all the researchers of UCAM DBA, whether you are in the final thesis stage or you are in the cohort 1, the new cohorts. So all of you are most welcome, and we have made it accessible to all of you. It's not just restricted to the thesis student who are writing thesis. So you can understand the kind of importance we are attaching, kind of focus we are giving, kind of strategy we have adopted in terms of bringing this statistical analysis unfolding before you to clear the mystery, to understand the basics of it. Many of you may be having quite a strong background on this, but many of you may not be having strong background. You may be more into qualitative, but then, in DBA, we prefer the mixed method approach. Okay, so that would be better in terms of justifying both the things. So when we talk about this, that means you need to bring in the quantitative analysis as well, along with the qualitative. So when you go to quantitative analysis, you have to do a lot of statistical, you have to, depend on statistical analysis, and you have to do it. So if you remember our last two workshops, what has been taken by Dr. Shankar was on the descriptive statistics, and some of them are inferential one as well. So you can understand that already we had 1 and 2 Dr. Shankar has taken. Prior to that also we had quantitative analysis workshop. But today we are going to be more specific on the analysis part of it, and we are going to bring you the T-test and Anova, the concepts, the fundamentals, basics, so that you understand that what it is and how it can be used as a researcher. That's very important, because once we have the clarity of understanding, and then we can move ahead, because no point just jumping into the software and doing it without understanding what we are doing. So with that kind of focus, we have designed this particular workshop. We sincerely thank and we appreciate Professor Dr. Neeta Yappan. She is our senior faculty. Many of you have already, already know her, because she has also delivered quite a few lectures to you guys in research methodology area. So that's the thing. So it's a huge thanks to her for agreeing to conduct this particular workshop. So without talking much on this, so let me hand it over to Professor Dr. Neeta to take the session forward. Over to you, Dr. Neeta.
Thank you, Dr. Abhijit. Hello, everybody. Good evening here from India, and good morning to you. Good afternoon and good evening, depending on your time zone, as always. I, Neeta Yappan, is happy to deliver this workshop, or rather be your facilitator for this workshop on T-test and Anova. Now, you're all researchers and you will all be collecting data, isn't it? And when you collect data, and as Dr. Abhijit said, as DBA researchers, we do encourage all of you to adopt a mixed methods approach. And you will have quantitative data as well as qualitative data. So when you say t-test and Anova, you're looking at, statistical methods for quantitative data analysis. All right. Okay. So I have not put the agenda here, but I'll briefly tell you. Now, let me tell you, nothing complicated. We're going to discuss a lot of basics so that you understand and we're not going to discuss softwares. It is not how you use a software to perform a t-test or Anova, but our focus will be on what these tests are, their usefulness, in what situations would you use them, and why should you use them. So this is basically so the when, how, where. All right. So this is basically, and what also. This is basically what we would cover. So now, what the first thing that we must understand before we do a test is the kind of test we adopt will depend on the kind of data that you collect. And there is a lot of data. Now, when you say, mixed methods as part of your quantitative study, invariably, many of us, or rather, many would be using a survey. Your data collection tool would be a questionnaire, and you will be collecting a lot of data using your questionnaire. All right. Now, the type of data that you collect can be classified into one. There are different ways of classification. It can be qualitative data, quantitative data. It can be categorical data, numerical data. It can be on the basis of scales of measurement. You can classify data as nominal, ordinal, interval, and ratio. All right. So let's see for what, we will be discussing t-test and Anova, but for what kind of data can you apply or use t-test and Anova? That's the first thing that we must understand. Now, you collect data, and the first, question that you ask is this numerical data or is it qualitative data? Any data which can be quantified as numerical data. All right. So this is categorical. It can be categorical. It can be numerical. Now, categorical data. When you have categorical data is, data which is put into categories. For instance, age, gender, all these are categorical. I'll give you a few more examples as we move on. And then, can the data be classified into more than two sets or only two sets? If the data can be classified only into two sets, as in, when you look at gender, assuming, there are only two genders, male and female, or let's say, athletes or non-athletes. All right. So you call that binary data or dichotomous data. All right. Now, if the data can be placed in more than two sets, then you ask another question. Can these data sets, can this data that you've collected be placed in some rank order? All right. As in, for example, your bachelor's, master's, doctoral degree. There is some rank order for that, isn't it? On the other hand, your college majors, when you say your college majors, you've majored in arts, you've majored in science or something else, there is no particular rank order. Any way you place them, it doesn't matter. All right. So there is categorical data which can be ranked and categorical data which cannot be ranked. Categorical data which cannot be ranked is nominal data. And data which can be ranked is ordinal data. Now, nominal data is just a name. All right. So for instance, let's say age group, your age group. All right. You say, let's say, let's take a case of children, youth, or children, youth, middle-aged, old age. So that is our children, youngsters, middle-aged, old age. So that's a group, and there's a particular ranking for that, isn't it? On the other hand, when you say, color of your shirt, blue, black, red, white. Blue, black, red, white is nominal data. There's no particular rank order for it. All right, so it's just a name. There is no natural order. There is no order in which you can place them. So it is nominal data. On the other hand, when you can rank them, as in the case of, we said about your degree, your educational qualification, your income level, even for that matter, when you look at age group, these are all ranked data. So that's ordinal data. These are basics. Perhaps many of you would know it, but I just thought I will begin with this as we move on to the t-test in Anova. So we're not really concerned about this data. All right. Now, numerical data can be interval data or ratio data. There's another classification also, discrete data, continuous data. We'll come to that. I'll show you that on another slide. So now, interval data is data which, when you may have more than two categories, and the difference between these categories are relevant. All right. So we assume that the difference between these categories are equal. For example, when you look at, income level or your education level, bachelor's, master's, you cannot say there's equal difference between them. All right. On the other hand, when you say, let's say, you're measuring temperature, isn't it? The difference between 10 degree and 20 degrees is the same as, the difference between 20 degree and 30 degree, isn't it? There is a difference. Now, in ratio data also, you will see the difference, equal, differences. But there is a small difference between interval data and ratio data. In the case of ratio data, there is an absolute zero. All right. Let me give you an example. Now, let's say, let's take temperature in, Celsius scale. In Celsius scale, I'm sure many of you would know that there is no absolute zero, because 0 degree does not mean absence of temperature. That is why we say, there is no 0 degree is a temperature, and a body, let's say an object is 10 degree, another object is 20 degree. You normally don't say, the 20 degree object is twice as hot as the 10 degree object. No, that is not right on a Celsius scale. But, those of you who have, who can recall the science that they learned in school will probably remember, when you probably, Fahrenheit scale, Celsius scale, and there is another scale, Kelvin scale. Even Fahrenheit scale does not have an absolute zero, whereas Kelvin scale has an absolute zero. So, on a Kelvin scale, you can say, something is twice as hot or twice as cold, or thrice as hot or cold. All right. So that's a difference. Let's say you take the case of height. You take the case of weight. You can definitely see a person who is 50 kg is twice as heavy as a person who is 25 kg. So that's ratio data. Or a person who is, let's say, 6 feet is twice as tall as somebody who is 3 feet tall. That's ratio data. All right. So in interval data, the distance between the different points are equal. There is equal distance between the different points, but the ratio is not the same. As in the case of, you would never say, I mean, what would you say about ice and boiling water then? Ice is at 0 degrees Celsius, water boils at 100 degrees Celsius. I mean, you can never say, that, isn't it? And you would never say a body which is 50 degree is, half as hot as boiling water. No, that is wrong. All right. So that's the difference between interval data and ratio data. So ratio data has absolute zero. And what it means is the absence is, if the value is zero, it shows a lack of attribute. Whereas in the case of interval data, if the value is zero or the measure is zero, does not, imply lack of the attribute. That's a difference. All right. So you have interval data and ratio data. And data again can be, this is what we said, continuous data and discrete data. Let me move to the other slide. I'll show you what continuous data. Discrete data is data which is measured in whole numbers. All right. So whole numbers, it's actually counted. This is actually measured. Continuous data is measured. Discrete data is counted. It's a count. For instance, you can see that here. This is quantitative data, numerical data. Qualitative data is categorical data. So discrete data, you can see that can only be, in whole numbers. For example, the number of the number of people in a, employees in a company, the number of cars that you manufacture. All these are discrete data values. On the other hand, when you measure your height, when you measure time, when you measure the weight, when you measure speed, all of this is, continuous data. All right. So you have discrete data, continuous data. We've already discussed nominal data and we've discussed ordinal data. All right. Okay. So now moving on. This is important because the type of statistical text. Now, just to give you, with this, you can use descriptive statistics. I was just listening to Dr. Abhijit saying that you had a workshop on descriptive statistics. Isn't that right, Dr. Abhijit?
Yes, yes.
Dr. Raman had taken. So,
Dr. Shankar has taken.
Yeah, sorry, Dr. Shankar. So, nominal data, ordinal data, which at best you can do is, you can use descriptive statistics. Whereas if you want to use inferential statistics, data has to be, quantitative data. All right. Okay. Descriptive is just presenting, some, describing the data. Here, it could be some other characteristics of the data set that you do. All right, with inferential statistics. Okay, now, so this is the same thing. This is again, adapted from the sources Saunders textbook. You can see that some of the tests, all right, just to be aware. I mean, it's nice to be aware of these tests. Our focus is going to be t-test and analysis of variance. Now, these are tests of difference. All right. Tests of difference. You want to see if there is difference. We'll see what difference. You may have a few groups. You want to see if there is a significant difference between or among these groups, depending on the number of groups. All right. So when you have only two groups, difference between two groups is you use a t-test. And if you have more than two groups, which is three or more, we, to find the difference among groups, we use analysis of variance or Anova. All right. T-test is also known as student's t-test. So if your, normality, okay, we'll come to normality. We'll come to, I'll quickly touch upon these, though we will not be, going into chi-square test. Let's say you want to find out if there is a relationship between income and gender, then you would use a chi-square test. Why? Because income and gender both are nominal, variables. Income is ordinal and gender is they are anyway, categorical data. Gender is a nominal. So you would use a chi-square test. All right. You cannot perform a t-test or ANOVA if both the variables that you have are are categorical data. All right. So then, here's a question for you. You're all familiar with Likert scale, isn't it? Is that right? On Likert scale, you may have, a few statements, and then you will ask typically something that many of you would use in your survey questionnaire, and you would ask them to, it could be a strongly disagree, a strongly agree scale, and so you will ask them to give their response on the various statements or questions that you have. You're all familiar, isn't it? What kind of data do you think? This is a scale, example of a Likert scale. What kind of a scale do you think is a Likert scale? Is it nominal? Is it ordinal? Is it interval? Is it ratio? These are the different points. Strongly disagree. This is a 5-point Likert scale. So these are the various points. Is it nominal? I hope I'm audible.
Yes, you are.
Yes, I cannot see if they are responses are coming in. I can see that. Yes, there's no rocket science in this. This is very simple. What kind of
Dr. Shankar has come back. Dr. Shankar has shared.
By coding, you can convert to nominal. Is that right?
Yeah.
Nominal is the lowest scale. In scales of measurement, nominal is the lowest scale. Do you think these are just names, or you think there is a particular order for this? That's the first question. Is there an order? Yeah, there is an order. Right. So there is an order, isn't it? There is an order. Now, do you think so? It is not nominal, it is ordinal. Now, do you think there is equal difference between strongly disagree and disagree and neutral and agree? Do you think the differences are equal? Yeah, you're right. The differences are not equal. All right. So typically, Likert scale data is ordinal data. All right. And there's a lot of controversy around Likert scale data. Now, if you look at typically the kind of questionnaire that you would use, we would all be collecting Likert scale. Invariably, most questionnaires have Likert scale data. All right, unless it is a pure finance or economics kind of data that you collect. So where observable, if you collect information or data on observable variables. Otherwise, when you have indicators, when you use indicators, typically it is Likert scale data. There's a lot of controversy around it. All right, now what we do is, but though this is ordinal, Likert scale data, there's been a lot of, there are some of the analysts who say, no, it has to be treated as nominal. Some of them, sorry, ordinal. Some of them who say it can be treated as interval. So if it can be treated as interval, yes, t-test and Anova can be performed on Likert scale. And that is how, it is accepted today. So what you do is you give these numbers, usually when you code, Dr. Shankar said about coding. So we usually code, all right? And the coding is usually from, strongly disagree is given a code of 1, 2, 3, 4, 5. That's how coding is done. All right. And when we code, and the assumption that we make is the difference between 1 and 2 is the same as the difference between 2 and 3 is the same as the difference between 3 and 4, etc. And this is how we convert Likert scale into an interval scale, and that is accepted in research. All right, unless your supervisor or your supervising guide, belongs to another school of thought and says no. Otherwise, it is accepted in research, and Likert scale data can be analyzed as interval data, which means you can perform t-test or Anova on Likert scale data. The reason why I mentioned this is because a lot of us, including myself, when I did my PhD research, my data was Likert scale data. All right, and I have performed t-test and Anova on the data that I've collected. Is that clear? All right. So this is something that you need to remember. It is by theory, it is ordinal data, but we quantify, assign these numbers, we quantify these, options, and then we say this is interval, and that is universal, around the globe, that is a norm, that is accepted. Okay, so that is Likert scale. Now, okay, moving on. So these are various tests. It's just for your information. So, when you look at tests, the statistical tests, it can be, we're looking at, inferential tests. Tests can be relationship testing, tests that you do. Testing differences, if there are differences among the various groups, test of differences, test of prediction, all right? And depending on the data type, if your data is categorical, we said even the relationship testing, if you want to see if there is a relationship between, so I'm taking the same example that we took up a little while ago between age and income, or gender and income level. So that's categorical, all right? So you do a chi-square test. Now, if it is continuous data, you do a Pearson correlation test, if it's a relationship testing, all right? If it is continuous, all right? Now, difference, categorical, continuous. Now, we'll come to continuous because this is going to be our focus of our workshop. So let's look at prediction, and then this is testing if there is a relationship between two or between two or among, three or more variables. It can be, if it's categorical, the kind of, test that you would do to test relationship is logistic regression. It's also, I think, referred to as, if there are two variables, binary logistic regression. And if I remember correctly, SPSS gives you the option of binary logistic regression. If it's continuous data, depending on, number of independent variables. If you have only one independent variable, you do simple regression. If you have more than one independent variable, you do a multiple regression test. Now, let's also understand these are only, there are, more sophisticated tests available today. These are all first generation techniques, all right? Because, computing power is increased tremendously. There are many softwares available where you can do, you can use the softwares for performing other more complicated tests, which are called second generation techniques. For example, when you look at structural equation modeling, perhaps some of you may have heard, those are, structural, SEM uses second generation techniques. All right. So coming back to this, I hope there are no questions. All right.
Yeah, one has come, which I was answering.
Okay.
Mujahid has asked, is it mandatory to have the 5 scale or 3 is enough?
Who's asked?
Mujahid.
Okay.
Mujahid has asked.
Yeah, Mujahid. Yeah, Mujahid. It's enough to have 3-point Likert scale, but what is? There are 7-point Likert scales, 9-point Likert scales, but to give a range of, to have a range of responses. Generally, if you look at Likert scales, a 5-point is more commonly used as, or is more popular. What happens with the 7-point Likert scale is it could cause a little bit of confusion in the mind of the respondent in terms of, you may have very strongly disagree, then strongly disagree, then disagree. Now, what is the difference between very strongly disagree and strongly disagree? Would you be capturing good responses or more accurate responses? So the more, points that you have, it could lead to, more confusions, as in, confusions in the mind of the respondent, not being able to distinguish between, two successive points. On the other hand, 3-point, there's nothing wrong, but in terms of the insights that you may come up with, it may be, it could be equivalent to considering a yes, a neutral, no. All right. It doesn't, it may not help you come up with too many insights. So 5-point is generally advised. Have I answered your question, Mujahid? It's not wrong. Yeah.
No, I think, Dr. Nita, you have answered very well. And then, that why they need to go for 5, because that gives them a better, choice of the things. That's right. and the expression of opinions. So that would be good, because 3 will be too less actually. That's what Dr. Shankar is also mentioning here.
That's right.
That 3 is too less for expressing the respondent's feeling. So we normally go with 5, as 7 becomes hard, as you said. So 7 becomes a little harder for them to handle. So it is better, Mujahid, if you go ahead with the 5. Am I right, Dr. Nita?
That's right. That's the reason why I said a 3-point scale is similar to a yes, neutral, no scale.
Yes, that's right.
All right.
Yeah.
Okay. Yeah. So coming back to this, now our focus is going to be continuous data. T-test and Anova are test of differences. All right. So test of differences, and the difference between T-test and Anova is in the number of, groups that you have. I'll come to that, number of groups. All right. So if you have only 2 groups, difference between 2 groups, you use a T-test. If you have more than 3 or more, or rather more than 2, 3 or more, and you want to find the difference among these groups. For example, if you want to find, let me give you an example. If you want to find the difference between males and females, you would use a t-test. If you want to find the difference between, let's say, three youngsters, middle-aged and old-age, you would use Anova. If there is significant difference among these three groups, could be on anything, in their brand preference or in their brand loyalty. Just taking a variable here, so you would go for Anova. T-test will not, you cannot perform a t-test if you have more than 3 variables. I hope that's also clear. All right. So I'm going to annotate. So this is going to be our focus. Okay. And we have two-way Anova, but we will not be going deep into two-way Anova. This is what it is going to be. All right. So moving on, I will have to now, I do not know. Can anyone help me with how do I move the slides now? I've got the pen and I'm unable.
You're unable to move the slide?
Yeah.
Okay.
Can you unpin this particular slide, Dr. Neeta?
I am unable to unpin, Simi.
Stop share and come back.
Yeah, I'll have to stop share and come back. All right, so give me a minute. This is it, okay? Okay, so I avoid annotating. All right, okay. Now, the assumption that we make for t-test, I'll tell you about, what this is. T-test in Anova, you can see here, I hope you can see the table below. You can see that t-test Anova figures in under parametric tests. All right. So these are parametric tests. Parametric simply means your data is normally distributed. All right. Your data is normally distributed means, I hope what a normal distribution is. It is you do not have values, tilting towards one side or the other side. All right. So let's say the mean value is, let's say 10. You will have equal number for a normal distribution, mean, mode, and median are at the center. If the mean value or the central value is 5, you will have equal number on either side of 5. All right. That is what normality is. So one condition is the data that you collect has to be normal. So you have to ensure normality of the distribution. Distribution is data that you collect. All right. So now normality of distribution, if you're using SPSS, SPSS gives you the option of testing for normality. I'll show you something, a QQ plot, before we wrap up. That's my last slide before the thank you slide. I'll show you what the QQ plot, looks like. So normality is important. Now you can see, you've collected, age in years. You've collected data on the age of respondents. Now you see this is normally distributed. You can see that. And typically normal distribution is a very important distribution. And we keep hearing about it because most of the things around us follow a normal distribution. Most of the phenomena follow a normal distribution. And there are many, probability distributions. Normal distribution. So this is what it means. If you look at, age of the DBA students who have enrolled, or the height of DBA students, weight of DBA students, marks scored by students, you will be able to find that you will be able to, run a distribution like this. So this is a histogram. You plotted frequency and, age. There are 40,000 with age 40. That is what it means. You'll be able to run a normal distribution. You can see that. All right. Now in this case, number of episodes of anything, like let's say of some event. Now you can see this is not. You will see that this is more skewed to the left side. Higher values are more skewed to the left side. So this is a left skewed or a negatively skewed. We call it a negatively skewed. Negative, I think it's negatively. So you have a negatively skewed, distribution here. All right. So you can see that normality. So that's one condition. So parametric tests assumptions are your distribution is normal. There is homogeneity of variance. Homogeneity of variance means the variation, let's say, the variation in age in one group will be more or less, say you have two groups and you want to see if there is, let's say marks scored. All right, let's say marks scored. So you want to see if there is a significant difference or in the marks scored by, two groups, two cohorts. All right. So homogeneity of variance basically refers to the variation in marks within the group. All right. So variation marks within the groups must be, approximately. There shouldn't be, large difference in the variation, within the groups, between the groups. All right. So that's it. And independence of observations, which means, the marks scored by group A shouldn't affect the marks scored by group B. All right. That is independence of observations. If, the data that you've collected follows these, then t-tests, Anova, and Pearson correlation can be done. That's what you see here. All right. Pearson correlation is a test for association, as we saw. And when to use data, these are corresponding non-parametric tests. If the data that you collect is not normal, if then what you must use is non-parametric tests. All right. One sample, you can see that some of these tests, I have it on another slide as well. All right. So you can, some of these tests are these: Mann-Whitney U test, Wilcoxon assigned rank test, Kruskal-Wallis test, etc. All right. So you will have, before you do your analysis, something that you need to do is you need to test for normality of your distribution. And you need to ensure that the data that you've collected is normally distributed. And you should, if it's normally distributed, you will not have, you should not have outliers. So if you have outliers, which is extreme values, if you have outliers, you must remove those outliers. All right. Okay. So moving on. Yeah. So these are now. But, just as we discussed earlier, ordinal data, Likert scale data is ordinal data, but yet you can convert it into, you can assume it to be interval, and you can perform, t-test in Anova, though it is theoretically ordinal data. Even if your data is non-parametric, you can use, not normally distributed, you can use parametric tests. These are a few, thumb rules for using, which is again, accepted. You can, if it's a one sample, there are different types of, please bear with me. I'll come to these different types of tests in a while. One sample t-test, if you're, if the number of subjects in your group or observations in a group is greater than 20, you can use, a t-test. Now, the reason behind this is that parametric tests have more statistical power than non-parametric tests. And that is why there is an insistence on collecting data or ensuring that the data that you collect is normally distributed. Because these parametric tests are more powerful, or statistically they are more considered to be more powerful than non-normal distributions. All right. Okay. So if it's a two sample test where you have two groups, each group should have more than 15 observations. Again, one way Anova, if you have, we said more than 3 groups. For this has to be actually 3 to 9 groups. Each group should have more than 15 observations. For you have these, so you can take a look at these. Okay, so now we're moving on to t-test and Anova. We're trying to understand what. Let me just take a look at the time. Yeah, so I think that's about 45 minutes. So when you look at it, these are 2 tests. T-test is also known as students' t-test, and Anova expanded is analysis of variance. These are statistical methods used in the testing of hypotheses for comparison of means. All right, difference. We said difference. Is there a difference in the mean value of that particular variable between the 2 groups? All right, if it's Anova among the more than 3 or more groups. T-test is used to compare the means. I'll take example, make it as simple as possible for you. Between two groups, and Anova is used to compare means among 3 or more groups. Now, what you need to have is, a requirement is you must have a dependent variable, all right? A dependent variable which is in continuous scale and approximately normally distributed. We said, our Likert scale, we said Likert scale is nominal. Likert scale, we said is, you can consider it to be interval scale, all right? So Likert scale item. So let's say you've captured brand preference. You want to see if brand preference differs among different age groups, or you want to see marks scored in exam differs among different cohorts, all right? So this is a dependent variable. Dependent variable is marks scored. It's a dependent variable. It is in continuous scale. Again, when you look at the other example, we said brand preference, all right? You can measure brand preference on a continuous scale. So that's dependent variable on a continuous scale. And your age group or your gender or your, all of these groups are an income group. All of these groups are, categorical, all right? So they should be normally distributed, all right? So t-test, this is a difference. Now, if you have only, we've already discussed this. Now, the problem with Anova is when you look at t-test, I'll show you, the output that you may get. I'll show you the SPSS output, and I'll also show you how you can interpret the output. Now, the statistic that we use is T statistic, and for Anova, it is a F statistic. We'll come to that, not to worry. Now, t-test will tell you if there is a significant difference between the mean values of the two groups. And it will also tell you how they differ. In Anova, you have, let's say, 3 groups. When you perform in Anova will tell you if there is a difference, Anova will tell you, yes, there is a significant difference among these 3 groups. Now, let's say you have A group, B group, C group. Anova will only tell you there is a significant difference between the mean, let's say, brand preference, mean brand preference among group A, group B, or group C, or, marks scored among cohort A, cohort 1, cohort 2, and cohort 3. It will not tell you which of these 2 groups, or, at least, it will tell you at least 2 groups are different. There could be more than, all groups may be different, but it will tell you at least the inference that we make is, at least 2 groups are different. But Anova per se does not tell you which 2 groups are different. All right. For that, we will have to conduct post hoc tests. There are many post hoc tests like Turkey test. I think there's something called sheep test. There is, we call that multi-comparison test, multiple comparison test. There is an LSD test. I'll show you one of those. Okay. Now, if you have only 2 groups, then the results of a one-way Anova and t-test will be equivalent. All right. So, so let's not look at that. Look at this t square, as you will find that, t square, the value of the statistic, the square of the t statistic will be equal to f. Let's not get into that. Okay. Okay. Now, let me also introduce you to, now, when you do sampling or when you do statistical tests, errors are unavoidable. Okay, errors are unavoidable. Just to give you an example, I'll take a very simple example and then go to the specific examples for t-test in Anova. Now, let's say you want to test if you're doing some business, let's say fruit business. All right. So let's say the vendor has delivered apples or oranges. Now, let's say 10 or 20 or 30 cartons of each carton with 1,000 apples. Now it's testing each of them is practically difficult. So what you will do is you will take a sample. So your inference on whether this is rotten apple or good apple or sweet apple or not will be based on a sample that you take. Now let's say you have 10,000 apples delivered, and in the 10,000 apples that's been delivered, let's say 50,000 are bad. in the 10,000 or 50,000 is not possible. 5,000 are bad. Now, when you draw a sample of 100, unfortunately, it may be possible that, when you draw 100 that you draw are all good apples, because that's a sampling error, isn't it? Are all good apples. And what is, it's actually a rotten, lot. But the inference that you make may be, that, apples are rotten. All, all apples are good. You may accept delivery. On the other hand, there may be only, 10 apples rotten. And you may put a condition, if less than 10, 10 or more rotten, I will assume that the entire, lot is rotten. So unfortunately, when you take a sample, all the 10 rotten apple may be in the 100 that you draw. So what will you do? It's actually a good lot, but you may reject a good lot. All right. Similar, so errors are unavoidable. Now, let's take, there are two types of major errors. Type 1 error. Are you all familiar with p-value? Have you heard of p-value, level of significance? I just want to say, you've all probably been, you've all probably been reading papers, research papers. Have you come across p-value? Okay, all right. So we'll quickly try to understand what p-value is. And, the reason why we're doing an ANOVA and not a t-test, let me tell you, when you have more than two groups. Now, there are two types of errors. Type 1 error, there are two hypotheses that you will always formulate. Now, not necessarily in your dissertation, you can just have one hypothesis. But, if you look at the science behind hypothesis, there are two hypotheses stated. Null hypothesis, now this is a test of difference. We will say there is no difference. An alternate hypothesis will be, the alternative hypothesis will be there is difference. All right. So null hypothesis always in test of differences, no difference. All right. So null hypothesis is, so because these errors, let's say we are, you want to test the difference, let's say two production methods. All right. So now you're using production method A. You've developed a new method B. And you want to know the effectiveness of this method. All right. So let's say, so the method is a categorical variable. And let's say effectiveness, there's some scale on which you measure. That's the dependent variable. Now, when you would want to measure. Now, the null hypothesis is there is no difference between the productive or the effectiveness of both groups, and the mean effectiveness of both groups. And the alternative hypothesis will be there is a difference. Now, it is possible that when you measure, your measurement may tell you that the new method is more effective, when actually it may not be, just as in the case of the rotten apples that we discussed. All right. So this is a case where the null hypothesis is true, which is there is no difference. But because of your measurement, the inference you draw is that they are statistically different. And so what do? You would, so you would reject the null hypothesis. That the null hypothesis is there is no difference. And you accept the, null hypothesis is false. Null hypothesis is true. All right. So what happens is, so this is you reject the null hypothesis, and then you say, yes, the second method is more effective. So what do? You implement the second method when it is actually not very effective. So this is type 1 error. In a type 2 error, what happens is there may actually be no difference, but you may assume that there is a difference. All right. So here what happens is we are always, in hypothesis testing, we are always concerned about type 1 error. All right. We're always, because type 1 error is more important because, look at the investment that you make. And you may not, it may not yield you the desired benefits. So we are always concerned with type 1 error. So at most, what we may happen if it's a type 2 error is we accept the fact that, there is, they both are equal. And then what we'll do is, we may improvise our method too. So that will, in a way, be advantageous to us. All right. Anyway, so at least in this scenario. So here what happens is type 1 error. So we always try to control, when we test hypothesis, we try to control the type 1 error and we set the value. All right. So when we control the type 1 error, what we're saying is that the null hypothesis is true is not, out of chance, or, we're rejecting the null hypothesis not out of chance, but, because it is, statistically significant. All right. And we usually set it as, if you can see this, the second image, you can see this is actually the p-value. All right. It translates into the p-value. And it is usually set at, 5% or 1%. All right. So when you say 5%, you're saying that only 5% chance that this is, or 5% probability that this has occurred out of chance. All right. With 95% confidence, you're saying that this is statistically significant. All right. So you'll come across this 0.05, p-value 0.05, as we look at, interpreting or understanding t-test in Anova. That's the reason why I thought I'll tell you what significance level is. All right. So traditionally, we try to set type 1 error to 0.05 or 0.01, which is 5% or 1%. And we say there is a 5 by 100 chance that the variation we are seeing is due to chance. Or we say there is a 1 by 100 chance that the variation we're seeing is, due to chance. All right. So that's the assumption. So I just wanted you to be aware of what the p-value is and it is relevant. Now, a question that you can ask here is, let me also tell you the relevance of the p-value. Now, what happens is, let's say, question that you can perhaps ask is, t-test is for, testing difference between two groups. Why not, when you have 3 groups, why not perform 3 t-tests, which is, let's say A, B, C. Perform a t-test for AB, perform a t-test for BC, perform a t-test for AC. Isn't it? That's possible. And then you can come out with inferences. But we do not do that. Because, there is, when we do it with A and B, there is a 5% chance. When we do it with, when we use the same group, A and C, we are increasing our type 1. We said type 1 error should always be controlled because that is more dangerous than type 2 error. And we set it, that's the reason why we've set it at 0.05. And there are rare cases when you may go up to 0.1. I'll come to that, that's a different discussion, altogether. Now, so what you say is, if you were to do a t-test again, you increase, though it's not exactly 5 into 2, but for few samples, it approximately translates into you are increasing your type 1 error to 10%. All right, which means only with 90% confidence, you're saying this is statistically significant. 10% chance that this difference that you see may be due to chance. Variation that you see may be due to chance. Now, if you had 4 groups and you had to perform 3 tests of, 3 or 4, tests, if for the same group you perform 3 tests, what happens is, approximately it translates into 15%, a type 1 error. So which means with 85%, the opposite of significance level is confidence interval. Or, so level of confidence. You're saying only with 85% confidence, there's 85% chance that is not acceptable. 85% chance that this is statistically significant. 15%, chance that this variation is, or 15% probability that this is due to chance. Okay. May I move on? Assuming everything is clear. Dr. Abhijit, I hope there are no questions. So type 1 error is generally reported as a p-value. This is something that you need to understand. Okay. Now, You're muted, you're muted, you're muted.
Okay, so sorry, Dr. Neeta. Actually, Daniel has come back and saying that type 2 errors can also be costly too. Okay, so that's what
Yeah,
he
type
is
2
saying.
errors can also be costly, but in hypothesis testing, our focus
Mhm.
is always on type 1 error, and we try to control type 1 error. The p-value that you always relate to is that you always relate to and you would be concerned about, and which on the basis of which you reject or accept a hypothesis is a p-value.
Mhm. That's right.
Okay.
Thank you, Dr. Neeta.
Yeah.
Let's move on. Yeah.
All right. So there are three types of t-tests. All right. There is one sample t-test, independent sample t-test, and paired sample t-test. One sample t-test is when you only have a group. All right. And let's say this is, all the DBA students of UCAM DBA students of Westport. All right. And let's say you are one cohort, cohort, let's say 25. All right. Now we have, RMAM, we have the average, assuming you had a test and average mark scored. Now, this is a population, the population average. Now you want to test if if there is a significant difference of the mean marks that cohort 25 have scored with the population average, then you use a one sample t-test. All right. So the comparison is between a sample and the population, or a value, given value, or a claimed value. Here, the claimed value is a DBA UCAM DBA students average score. All right. When you're comparing between cohort 24 average mark scored between mark scored between cohort 24 and cohort 25, you have two groups. You call it an independent sample t-test. All right. Now, when you're comparing, this is a paired sample. Here, you'll be able to pair the observations that you have. All right. So you want to know if there is a significant difference in let's say, the marks scored by cohort 25 students in test 1 of RMAM and test 2 of RMAM. All right. So you have, the marks scored in mean marks scored in test A, mean marks scored in test B. You find that, difference of each student, and you find if there is a significant difference for a significant difference. All right. We'll take a look at all of these in detail. All right. So there are three types of t-test: one sample t-test, independent sample t-test, and paired sample t-test. One sample t-test is relatively very simple. So let's say, let me take this up a little bit. Yeah. So you have let's say some test, RMBM, some test, you were, this maximum you could score was 4. So let's say all DBA students, 5, I think we've crossed 500. So population is 500 students, and claim score is 4. And mean score, you've taken, let's say your cohort size is 40, means you've scored 3.72. Now, there is a difference. You want to test statistically if this is statistically significant. So it's difference 3.72 and 4. All right. So your null hypothesis is sample mean is equal to the given reference value. Reference value is 4. And the alternative hypothesis is sample mean is not equal to the given reference value. Okay. You're all there with me, right? What are the, Mujahid, it could be any, I'll come to that. It could be any factor. And these categorical variables, as you rightly said, are referred to as factors. And let's say you have male, female, or you have, different age groups. You call those levels of factor levels. All right. Now, I'll come to that. That you as a researcher, you will have to, appropriately decide what categorical variable you need to use. We'll come to that. Okay. Yeah. So coming back to this, okay. Now, coming to softwares, there are many softwares you can use. SPSS will give you results. Microsoft Excel can be used. R as an open software, R can be used. Then Python, you can do, the testing of difference using Python. Then there are many other online softwares. I think Statisty, Data Tab. These are all softwares using which you can do these test of differences. Now, I'll show you, how the kind of output SPSS will give you. This is the kind of output. This is the output when you okay. So how you do it is, you go to compare, you go to analyze, compare means, the analyze tab on SPSS, compare means, and you choose, all these tests are there. You choose one sample t-test, all right? And after you perform, enter your variables or enter the values, this is the output that you will get. Now, let me tell you what this output means, all right? So this is, if you can recall, our sample size was 40. You can see that 40 here. The mean is 3.72, isn't it? Standard deviation, I hope you know what standard deviation. Standard deviation is a single measure which tells you the, it's a measure of dispersion. The different, the variation of individual values from the mean value, all right? So that's, one single measure which tells you it's about 0.73. All right. Now, I'm not going into all of these. Degree of freedom for one sample t-test is n-1. Here, n is sample size, -1 is 39. Let's not get into all of that. Let's look at, what is significant. Okay. Now, coming to this, there are one sample. We have, we're looking at two-sided p-value. Since we have one-sided also here, let me tell you the difference between one-sided and two-sided. One-sided is, directional. For example, men score higher than women, or men do better, women do better than men. That's directional, isn't it? There is directional. So if it's a directional hypothesis, you use you do a one-sided test. Now, in our case, there is a difference. We are only saying there is a difference, all right? Or if you say, now in this case, if you say the cohort mean is higher than the population mean, it's a one-sided p-test, significance test. Or if it is, now in our case, we say there is a significant difference between the group average, cohort average, and the population average. Then it's two-sided, okay? And so remember, the reason why I told you this is, remember how you state your hypothesis. Do not, simply state your hypothesis. It can make your, analysis a little, it can bring in a little bit of, vagueness to your analysis. Mm-hmm. So if you are referring to the two-sided p-value, two-sided test, then you must, state your hypothesis accordingly, all right? So now look at this. What we're concerned about is, we would look at this, p-value. I hope you can see my cursor moving, all right? So if you look at a hypothesis is, there is significant, there is no difference. Null hypothesis, alternative hypothesis is, there is a significant difference. Now, when, how do you make inferences? If your p-value, type 1 error, all right? P-value is less than 0.05. All right, then we're saying with more than 95% confidence, we're saying this difference is not out of chance. It is statistically significant. All right, now you can see here that the p-value is less than 0.05. And the inference that we say is, means there is a statistic, this difference is statistically significant. And we know the mean score of cohort is lesser than the the cohort score is only 3.72. The all this population score is 4. And we say the mean score is significantly lower than the cohort score. And you can see the difference. The difference is, this is, standard deviation, you have it here, 0.74. So this is 3.72 plus minus 0.04, 0.74. Any questions on this? So this is the inference that you draw. There was a statistically significant difference between the means. Therefore, we can reject the null. And therefore, what we do is we reject the null hypothesis, accept the alternative hypothesis. Any questions?
Sir. I thought that because we're doing a type 1 test, we can only say that there is not significant evidence for us not to accept the null hypothesis. But when you said you accept the alternative, no, can you really say you accept as opposed to, because you only could accept if you do type 2
Yes.
No. Test.
Or I can get you, Daniel.
Okay, Dr. Neeta, what Daniel is asking precisely, it's given here, why are you accepting the alternate hypothesis?
Because,
yeah.
So because, with more than 95% confidence, it's only, if it was greater than 5, if it was greater than 5%, it means that, with let's say 95%, 5% chance that, or 6% chance that this has occurred, due to, this is a chance occurrence, this is difference that you see. When it's less than 5%, we say this is not a chance occurrence. This variation is statistically significant.
No, that's not the essence of my question. What I am saying is that in fundamental statistical practice, we do not normally use the term accept. Yes. You're saying
but we do not use it. You're right. We say supported or not supported. We do not say accept or reject. We say supported or not supported. That's all we say. Have I answered your question, Daniel?
Yes.
Yeah. So, that's a wrong usage. Accept the hypothesis, reject the hypothesis, but it is commonly used. The correct usage is supported, not supported. So in your dissertation also, when you're doing hypothesis testing, try to avoid using accept and reject. Though it is very commonly used, the right usage is supported, not supported. You're right, Daniel. All right?
Yeah.
Okay. So yeah, this is a one sample t-test. In 2 sample t-test, you have cohort A, cohort 1, and cohort 2. Now, this is the mean, score of cohort 1. This is the mean score of cohort 2. And you want to know this, so these cohorts have been drawn from, the DBA UCAM students. Now, you want to see if there is a significant difference between the mean marks, average mean marks scored by cohort 1 and cohort 2. All right. So that's what, and the null hypothesis, the mean in the 2 groups, there is no significant difference in the mean marks of the 2 groups. There alternative hypothesis, there is a significant difference between the mean scores of the 2 groups. And here is the results that you will get. This is the output. All right. So cohort 1, cohort 2. You can see that there are 10 students each. Now, again, when it comes to the group size, ideally, they should be equal. It is okay even if they're not equal, because, when you look at cohort 1 and cohort 2, it is possible that they may not be equal, in terms of cohort strength, but it must be balanced. If it's, if the variation in the numbers is too large, it may not, give you the good results, or your interpretations need not necessarily be right. Now, let's say this particular test was out of, 12 or 15 or 20. All right. Now, in cohort 1 had 10 students, cohort 2 also had 10 students. Now, you can see this is, so when you have 2 groups, you conduct an independent samples t-test. All right. So that's the option you must choose. Analyze, compare means, take independent samples t-test. So, and when you do the analysis, this is the output that you get. These are 2 tables that you will get. In fact, this is 1 table, but it got cut. All right. So now when you look at it, this is your group statistics. Now, this is the mean marks scored by group cohort 1, mean marks scored by cohort 2. Now, you want to test. You are interested in knowing whether, this 10.2 and 11, if this difference is significant. All right. So this is the output. Now, here it gives you the F statistic. All right. So what you will be looking at is, you can see the number of, and the mean scores. All right. Now you can look at, okay. Now you will see equal variances assumed and equal variances not assumed. All right. Equal variance refers to the variation marks in cohort 1 and variation marks in cohort 2. If the range of marks, they should be equal. If they're not equal, you choose a lower row. If they are equal, you choose the upper row. How do you take a decision on that? That's given by the F statistic. All right. So you take a look at the F statistic. All right. And this, when you look at this F statistic, you look at this value 0.334. 0.334. All right. Now, if this value is greater than 0.05, which is, p value 0.0, the significance is p value. If this p value is greater, you can see, I hope you can see the, 0.334 here. If this value is greater than 0.05, then what you do is you will use equal variances assumed. You will use the first table. All right. If this value is less than 0.05, you will have to choose this row, equal variances not assumed. All right. So now, and then you will have to look at, you can see the level, significance level. The level of significance is 0.004, which is less than 0.05. So you will say your null hypothesis is not supported. You will accept the alternative hypothesis. All right. So the inference that you make is, yes, there is a statistically significant difference between the marks scored by cohort 1 and cohort 2. And we would say cohort 1 has scored, the difference is, you can see the standard deviation. So you will say, you will say cohort 1 has scored lower than cohort 2. Have you understood?
Dr. Neeta, can you come back to this again? Because,
right.
Can you come back to this? Yeah.
Let me show, let me begin. First take a look at, this is group statistics 5. First take a look at the F value. All right. F value, and if the F value, all right, is, the P value associated with the F statistic. This is, the F statistic. If the P value is greater than 0.05, then use the equal variance assumed row. If it was less than, we would have used equal variances not assumed. Now here it is greater than, so we will use this row. All right, equal variances assumed. Now that's the first thing that you must do when you look at this table. Then take a look at the T statistic, the P value associated with the T statistic. The P value is less than 0.05, which means we say your null hypothesis is not supported. All right. So you accept the alternative. Because it is not supported, you say we accept the alternative hypothesis, which means there is a statistically significant difference between the average marks scored by cohort 1 and cohort 2. And we can definitely say cohort 1 has scored lower than cohort 2. Which is, have you got it?
Yeah. That's now more understandable. Yeah. Now there is a question, Dr. Neeta. If you allow, then I can tell you this question.
Sure.
Mujahid has asked, what is the F value? F value, and how can we generate?
Which F value? This F value?
What is the F value, and how can we generate?
Okay, do not worry about the F statistic. I'll tell you about the F statistic, and the F, when the difference among groups, I do not know about a T value. I can tell you about the T value. When the difference, grows larger, the T value, you will see that the T value grows larger. All right. So I cannot really give you an explanation for what the F statistic is. All right. So what you'll have to look at is the significance associated with the F statistic.
Okay.
Is that okay?
I think that's right. Yeah. So it's okay. Go ahead.
It's a statistic associated with the difference between these means 10.28 and 11.08. That's at best what I can tell you.
Okay. Okay. Okay.
All right. It's a
Okay.
statistic, so it's a value associated with the difference in, these values.
Mhm.
Difference in mean, which is 10.28 and 11.08.
Great.
And we will also say, the confidence, when you look at, there's also another, with 90, you can see that 95% confidence interval. What we say here is that, if, again, let's not get, if the confidence interval, now you can say, minus the difference, what we see is difference in mean with 95% confidence, we are saying the difference in between cohort 1 and cohort 2 ranges between, now this is lower, that is why you have a negative sign here, ranges between 1.3 and 0.29, the range of values. All right.
Okay. Yeah. Okay.
May I move?
Yeah, please go ahead. Yeah.
Okay. Now it is a paired sample. Now paired sample t-test was used. We saw, let's say, you are providing a training. So pre-training, post-training scores, how employees performance. You're measuring employee performance. That's your dependent variable. And your categorical variable here is, pre-test, post-test. All right. Or here it is, test 1 and test 2. Now, let's say RMA, test 1, 2 tests. Now, students have scored, let's say A, B, C, D, E, F, G are students. Mean score is 82.75, and I think here it is 64.45. Now, you see, you want to know if this difference is, statistically significant. All right. So you can pair. You can see that, you can pair the subjects in the two groups on some basis. All right. So this is student A, this is student A, student B, student B. All right. Now you will calculate the mean score here. You will calculate the mean score in test 1 of ABCD, and the same ABCD students, you will calculate the mean score. All right. And now here it is, for each of them, pre-test, post-test. All right. Now what you do is, your null hypothesis is there is no difference between the mean value. Your alternative hypothesis, mean values of the two dependent groups. These are dependent groups typically. All right. So are different. Now you can see this is, this is the result that you will get. Okay. Just wanted to tell you here, if you look at what degree of freedom here, it is D1, N1 plus N2 minus 2. Let's not get into that. I cannot really further explain what the degree of freedom here is, statistically. All right. So you can see that test 1, test 2. All right. There were 398, the same subjects, 398 students were subjected to test 1, test 2. In test 1, they scored 82.74. In test 2, you want to know if this is statistically significant. Now, SPSS also gives you, the correlation between, the test 1 and test 2 scores. All right. The mean scores. All right. So you can see 0.243, 0.000. Now, sorry, significance. So you see, there is a small correlation, weak correlation between test 1 scores and test 2 scores. The p-value is less than 0.05. So, there is a small, there is a weak, 0.24 is a weak correlation. All right. Okay, that's not much of a worry for us. Here, this is what we see. Here, what we see is, this is, so you have the mean, test scores, isn't it? You have the mean test scores. You have, and you also have the standard deviation. All right. How these, which is an indication of the range of values. Now, then what you must see is, you have the number of valid cases, 398, 398. Now, this is the, difference. All right. This is the mean paired difference. This is the mean difference between the, scores. Test 1 score and test 2 score, mean difference. All right. So you have difference for each student, and the mean difference is 17.3. Student A, you have the difference. Student B, you have the difference. Student C, you have the difference. Student D, you have the difference. 17.3 is a mean difference, and with a standard deviation of 17.3 plus minus 9.5. That is how the marks or the scores vary. All right. Now, you then take a look at the T statistic. All right. You take a look at the T statistic. T statistic is, and for the T statistic, look at the significance value, P value. The P value is 0.000, which is less than 0.05. So what you will say is that your null hypothesis is not supported. So you will say, therefore, you accept the alternative hypothesis. Now you say, there is a statistically significant difference in the marks scored by students, RMAM students, in test 1 and test 2. And students have scored, higher, all right? Students have scored higher marks in test 1 than in test 2, all right? Or test 2, is about 17.3 marks more than test 2 average scores. Is that clear?
Yeah.
I hope no questions.
Do
not worry too much about interpretations. Interpretations can be a little, confusing now.
Yeah.
There are many tutorials. Don't get confused. So these are, I'm just telling you the relevant values. All right. Look at n number of valid cases, the mean value, standard deviation. So when you think of the standard deviation, you must be able to visualize the spread of values. 82 plus minus 6.8. That's how the value the marks range. 65 plus minus 8.46. That's how the marks range. So that's what basically the standard deviation tells you. The mean difference is 17.3, and the difference, ranges from 17.3 plus 9.5 to 17.5, 17.3 minus 9.5. And paired sample, very simple. All you have to look at is the level of significance and the T value. Dr. Abhijit, before you read that question, just one more. And with 95%, confidence, you're saying the mean difference, in test scores varies between, in the mean test scores vary between 16.36 and 18.2. Now, let me also tell you something. If between the lower and upper, 0 appears, then it is not statistically significant. And I don't want to get into that and confuse you. So this is the inference that you can draw from the confidence interval. Not much of a, worry. You learn that when you, write your inferences, but this is the interpretation that you can make. Yes, Dr. Abhijit, I'm sorry.
No, that's all right. Thank you so much for explaining. Now, Dr. Sufi has asked one question. Do we need to read T value here as well? 36.313. That's what.
Yes, you need to report your T value as well. You will have to report T value as well. I have put an example here. This is how you report. In fact, depending on your the referencing system that we follow, you can see that your mean score was lower than the normal score, a statistically significant difference of 0.28, 95% confidence interval, the value ranging between, the mean difference varying between, you can see that 0.04 and 0.5. T value at 39, you can see that where is the T value for degree of, this is the T value for the 39 degree of freedom, 39 is equal to 2.381, and the level of significance is 0.022. This is how you will have to report all these values.
Yeah.
There are so many online help websites where you can more than reporting. First, interpretation. You should know the interpretation. What are you doing? And should you be doing?
Yeah.
Now, earlier the question was asked, do I use age or gender? Now, when you're doing a business, you're doing a business research, isn't it? Something related to your organization. What age and gender, are they relevant demographic variables? Now, when you look at, something in marketing, perhaps those are relevant variables, isn't it? Age, gender, those are relevant variables. When you're doing, should you even capture those demographic variables? A question that you must ask. On the other hand, when you look at designation, you may be interested in, let's say, work-life balance. Is there a significant difference among, different, people in different, management roles? Or different roles in the organization, or at different levels in the organization, in their work-life balance? Perhaps you can come up with some insights. I'll discuss that towards the end. All right.
Yeah, please go ahead.
Yeah. So that's a wrap of yeah, okay. So remember, in paired sample t-test, measured values are available in pairs, persons independent. So this is not the same group, persons independent of each other. All right. Now, we'll quickly take a look at the data requirements. All right. Dependent variable, that is continuous. Independent variable, that is categorical. Nominal or ordinal, and as exactly for t-test, only 2 categories. Cases that have values in both the dependent and independent variables. All right. So independent samples, which is independence of observations. Observations in one group should not affect the mark scored. So, mark scored by group 1 should not affect the mark scored by group 2. Or test in, mark scored in test 1 should not affect mark scored in test 2. All right. So independent of samples, random sample must be randomly drawn, because only then, you can bring that normality, normal distribution of the dependent variable for each group. Homogeneity of variances, that's what we said, the variation, should not be, between groups should not be too different. All right. No outliers. Now, these 3 using SPSS, you can test. No outliers, homogeneity of variances, normality of distribution. If you can ensure these 3, the other 2, which is random sample, independence, all of these can be ensured. All right. So these are data requirements. I hope you have no questions on data requirements.
No questions so far. Yeah.
All right. Okay, so these are a few examples: 1 sample t-test, 2 sample t-test, paired sample t-test. And let me tell you, it can be very confusing. Even now, it can be confusing. Do not worry, that happens to everybody, unless, when you use this, in a big researcher, always conducting, research and performing these tests. Maybe this is like a, holy book for you. But otherwise, all of us, tend to get a little confused. But the difference is important. So here are a few examples of scenarios in which you can use. Now, again, let me tell you, if you're interested, let's say, you're doing something in HR, all right, work-life balance. Maybe, work-life balance between men and women, male employees and female. You can do all your hypothesis testing, prediction, regression, correlation, and all that. But since you've captured demographic, variables, this is something that you can do, and you can come up with some insights. And if you find that they statistically, you say, women have, let's assume, no gender discrimination here, and I don't want to stereotype. Let's assume, your hypothesis tells you, testing, or your results tell you men have more work-life balance. You can perhaps try to give some kind of explanation. This is because men, in this, the context of your study, in this particular industry, or in this particular company, or in this region, this is it. You can give some explanation. And ideally, you should all do that. Do not limit your demographic just to descriptive statistics. You must be able to do this test of difference. All right. Okay. Now we're moving on to Anova. Have I taken more than? Yeah, I have half an hour more. Okay. When Simi asked me, I told her I may, take only 1 hour. All right. Okay. So here's Anova. There are, 4 different types of Anova. We're going to limit our discussion only to one factor Anova, or one-way Anova. All right. So 1 factor, which is, you have only age. Now, two factors, let's say age and gender. One factor with repetition, so you do before, after, before, after. So I'm not getting into that. I must also confess, I'm not prepared to maybe even answer too many questions on that. All right, because I've not gone into that level, and I mean, I've learned it, I've seen it, but for today, I'm not well prepared to answer your questions. In case you have any questions on with repetition, all right. So all right. So this is factor one. This is what two factor is. It could be age and gender. All right. Or let's say, it can't be gender unless you have three genders. So it can be, more than three groups. All right. So it can be age and designation. All right. Okay. Now, this is what variance is. Now you can see, variance must be balanced. Homogeneity of variance must be there. Now you can see this is variance within groups. This is within group, variance is small, but you can see where you'll come across these terms in the resultant, when you see the output of the software. That's the reason why I'm putting this. Now here, variance between, look at the difference in mean, variance between groups is too large. Here, within groups, variance is large, between groups, variance is small. Okay, all right. So now we are interested in, let's say we are interested in, we have 5 groups here. Now I've taken this from my own thesis, all right, my PhD thesis. I'm going to take another variable here. My variable was a situational trigger, which can trigger that causes, that can trigger your intention to switch retail banks. So let's look at it as brand preference. All right now. So you have 5 age groups here. As is the case with, in a t-test, null hypothesis, mu is a Greek symbol for mean. So there is no significant difference in the average brand preference among the groups, or brand preference among the different age groups. That's your null hypothesis. Your alternative hypothesis is there is a significant difference in the brand preference, all right, among different age groups. And what you do is, you go to analyze. If you're using SPSS, analyze, compare means, you have an option, Anova, one-way Anova, choose one-way Anova. All right. And this is the kind of result that you will get. All right. This is the kind of result that you will get. Now, I hope I can remember all that I had, okay, in my thesis. Okay. Here, what you have is, do not worry too much about this. Okay. Now, between groups, all right. Now, this is the first table, descriptives. Now, you can see the number in each group, 63. Let's say we've measured brand preference. The mean brand preference for 18 to 25 age group was 2.02. For this one, it was 2.11, 2.3, 2.02, etc. All right. So these are mean brand preferences. So you can see the number, all right, in each group, 63, 133, 150, totally. So this was a total, mean brand preference for the entire group of all 385 respondents. I have 385 respondents, all right. Now, this is, that is what your groups, and it will also tell you the standard deviation. It will also tell you the range of, the mean, all right. So lower bound, upper bound, you can see minimum was 1 on that. This was a Likert scale. Let me tell you, this was a Likert scale data. All right. So mean, all the other examples that we discussed, marks are not Likert scale data. So here we assume that Likert, quantified, and ordinal data, we're treating this interval data. And that's exactly what I've done. Now, that's a first table. Now, when you look at this table, all right, you have variability of means between groups and within groups. Now, your level of significance, you can take a look at the level of significance. It is, between, you can see that it is less than 0.05. All right. So the F statistics, take a look at the F statistics, and the p-value associated with the F statistic is less than 0.05. So the assumption that you make is that, your F is significant. All right. So if your p-value is less than 0.05, the assumption that you make is at least between, between one of, at least between two groups, there is a signal. So you take a look at the F statistics and the p-value corresponding to that. At least between two groups, at least, there could be more. At least between two groups, there is a significant difference in mean brand preference. Now, remember I told you, Anova does not tell you which among which of these groups these differences are. You see these 2.02, 2.11, 2.35, 2.2. Among which of these groups the difference is statistically significant? It does not tell you there. It stops with that. So for that, we need to do post hoc tests. All right. So this is, multiple comparison test. So I have done an LS. I had done, in fact, I've, taken this screenshot from my own thesis, an LST test. All right. Now, an LST test. Now, what you must do is, again, you take a look at the, p-values. All right. This is, assuming brand preference. All right. You take a look at the p-values. All right. You take a look at the p-values. Now, between this shows, the difference between your 18 to 25 group is being compared with the other groups. All right. Now, when you look at this, you can see that, the 18 to 25. Okay. Now, here the inference that you draw is that if the p-value is less than 0.05, here, now, when you look at, the 36, compare 18 to 25, the 36 to 45, the p-value is less than 0.05. Now, you say, yes, there is a significant difference in mean brand preference between the 18 to 25 group and the 36 to 45 group. There is no statistically significant difference in mean band preference between 18 to 25 and the other age groups. Now look at 26 to 35. Look at the significance value. You can see 36 to 40. No, you can see this is 0.01. It should be less than 0.0, less than 0.05. Now you can see, between this, isn't it? This group, it is only 0.01. So now you say there is a statistically significant difference between the mean brand preference of 26 to 35 group and the 36 to 45 group, because the p-value is less than 0.05. Now, if you look at all the other p-values, now 36 to 45, you can see 0.01. We've already inferred this from here. 26 to 35, 36 to 45. That inference has already been done. Now, 46 to 59, all p-values are greater than 0.05. Here again, all p-values are greater than 0.05. So the inference that we draw is that here, yes, there is a significant difference in mean brand preference between the 18 to 25 age group and the 36 to 45 age group, and between the 26 to 35 age group and the 36 to 45 age group. As much as you say this, you should also be able to give some explanation. The 36 to 45 age group, this is, we see that there is a difference in their brand preference, maybe because, these are people, I'm just, hypothetical case, 36 to 45 are people who are peaking in their, career. So they have, more maybe disposable income. It may not be true, it may be true, but I'm just giving you an explanation for the sake of giving you an explanation. All right. So you give an explanation. So this is, some rich insight that you are having from the data that you collected. And let me tell you, usually what we see is, when you look at your dissertation, you capture a lot of demographic variables, and it is limited to descriptive. You say 35% were males, 65% were females. Beyond that, not much is done. But since you capture, and this doesn't take any time, you should all be able to perform this as well. All right. This is my, okay. So this is data, same, data requirements. You must have the differences. There you must have at least two groups. Here you must have two or more groups. With two groups also you can do, but t-test is advisable. And if an Anova will also give you same result, but you may be asked, why did you do a t-test? If you have only two groups, go in for Anova. and same, the data requirements, except that independent variable that is categorical must have more than 2 groups. All right. So this is how, as when you're using SPSS, you can test homogeneity of variances. All right. You can see this is the box plot. Now you can see this shows that, there is a large, variance. You can see this is a variance within the group. So variance within group is also, here variance is small, here variance is large. Between groups also you can see group means. All right. So accordingly, the Levin's test will give you, all right, that there is difference. The statistics will show you that accordingly you may have to use equal variances not assumed. All right. So so this is again the QQ plot for normality. This is the theoretical. If it is normally distributed, this is this straight line that you see. That is how these are the value observations. It'll fit into that line, the theoretical line. Here it almost fits into. So you can say your data is normally distributed. You can even have your histogram as an output. So that's it from me. Thank you all. If you have any questions, I'll try to answer the questions.
Thank you, Dr. Neeta. Thank you. Wonderful presentations. We all enjoyed and we got the feedback as well. Thank you very, very much for your presentation. Guys, now the floor is yours. So if you have any question, please do come back. And I appreciate the inputs shared by other faculty here, Dr. Shankar, Dr. Fernando, Dr. Raman. They all have shared. Dr. Sufi is also here. So thank you all very much for your inputs, which has certainly enriched. But then, Daniel, thank you for asking questions. So the floor is open now for question answer session. So please use this Q&A session. If you have any doubts, don't feel very shy in putting your questions over here, because it's not that everybody expect you to be an expert over here. As Dr. Neeta has said, that you need certain amount of time to come out of the confusions and clarity and all those things. Dr. Sufi has come back. Thank you. Doc, do we need to mention null hypothesis, or is it not enough we state only the hypothesis what we want to test? Alternate. Dr.
Yes.
Neeta.
Yes, we need not state the null. We usually state the hypothesis we want to test. That's all. But the theory is that there is a null hypothesis and an alternative hypothesis. And when we test, we use a p-value. And this is how, we try to see if depending on the p-value, we try to see if, what we do is does the p-value tell us that the hypothesis is supported or not supported? Null hypothesis supported or not supported? That's actually the test. It's enough to state the one hypothesis.
Okay. Thank you very much. And Dr. Neeta, Wisam has come back. Many a student is conveying their sincere thanks. Let me read out the name: Peter Fang, Nancy Rees, Zolil, Charity Dubey, Wisam Musaid, Dr. Sufi, Dr. Mania, Dr. Fernando, everyone. I mean, it's wonderful. Such a nice session. We are delighted. And we look forward for many more your sessions, because this kind of session is so important for DBA researchers or the researcher as such, okay? Because whether we are going for the qualifications or not, irrespective of the fact, because the research journey is on, and we are also writing a lot of research articles here and there. So this clarity, even many times we need it to bring this perspective in our research to make it more better research article, which can be published in Scopus. So from all sides, if you look at, we got the utility of this particular workshops, or we can use it to our advantage, the students, faculty, everyone. I mean, that's a wonderful insights, and we look forward for many more sessions from you. We will definitely a little bit tease you or disturb you, that Dr. Neeta, because it's quite infectious in terms of getting knowledge and such an authentic way you have explained it. So thank you so much. And there is nothing more. Johannes has come back. Thank you for the informative sessions. Dr. Raman has come back. Very insightful session indeed, Dr. Neeta. Great effort. So it shows the kind of, popularity, or I'll not say popularity, but the kind of thing it has touched in the mind of the people, in terms of effective knowledge sharing, what you have done. So thank you very much, Dr. Neeta, once again from our side, from DBA team. Thanks to you and Simi for organizing it. Thank you very much. Okay, all the very best. So we
Yeah.
look forward for many more sessions from you. Yes, Dr. Neeta, please go ahead.
Before you close, Dr. Abhijit, I must thank the DBA team for having given me this opportunity. And I thank all the participants today for the support you've given and for the questions that you've asked. In fact, I must tell you, I had to put in a lot of thought into preparing the presentation as to, because I know it's not, I mean, I must confess, as a researcher, I really didn't, yes, when I started doing my analysis, yes, I got a hang of it, but then, I had to put in some effort in thinking through us, put my feet into early researchers' shoes, and then see how it had to be, the presentation had to be prepared. I did revise a lot of things, went back to, a lot of things. So I must thank you all, and thank you all very much.
Thank you, Dr. Neeta.
Yes, your appreciation. Thank you very much for all the appreciation and your kind words. I'm humbled.
It's we really mean from heart, and you deserve it so much. And Dr. Neeta, what we liked in your this thing's approach is the simplicity and the application. So you brought the concept in a very simple, illustrative manner, and which is required, and then you clarified a lot of questions, and our colleagues here, Dr. Raman, Dr. Shankar, Dr. Fernando, Dr. Sufi, all they have shared their valued inputs. So together, if you look at, we have very effectively shared the knowledge to our students, and I'm sure that this is going to add value as we are getting the feedback from students here. So wonderful. Thank you very much once again to you, Dr. Neeta, and all the participants here, including the students and the team. Thank you very much. Have a nice day, everybody.
Yeah, all of you too. Thank you. Bye.
Thank you.